It began with a whisper, a flicker on a screen deep within the control room of the European High Energy Research Facility, EHERF. On March 30th, 2026, we were on the verge of a breakthrough, accelerating protons to unprecedented energies. The room buzzed with anticipation. Scientists from around the world focused on their monitors, faces aglow with data from the edge of creation. No one noticed the flicker, a single data point among trillions, dismissed as a statistical anomaly. This was no ordinary lab, a 27-kilometer tunnel buried beneath Switzerland, where protons raced at nearly the speed of light. We believed we had mastered the universe's most powerful forces, with redundant systems and AI monitoring every nanosecond. That fleeting data point was the universe's quiet reminder that our control was an illusion. Moments later, a second flicker appeared, this time from an adjacent sensor. The AI logged the correlation but deemed it within error margins. On the main screens, everything looked perfect. The symphony of physics continued. But deep underground, a single magnet was losing its grip. The whisper was becoming a murmur. The stage was set for catastrophe, born from the smallest of errors. We were blissfully unaware. The illusion of control was dissolving, millisecond by millisecond. The universe does not yield its secrets without a fight. Our mastery was about to be tested. The first sign had come and gone, unnoticed. Disaster was already in motion. To understand the disaster, you must understand the machine. A particle accelerator is a cosmic racetrack, hurling protons at near light speed. Steering is the real challenge. No walls, only powerful superconducting magnets, colder than space itself. These magnets, lined along the tunnel, create magnetic fields thousands of times stronger than Earth's, gripping the beam with staggering precision. A deviation of a millimeter could be catastrophic. Tens of thousands of sensors monitor every variable, temperature, pressure, beam position, feeding data to AI in real time. The system's safety rests on this network's integrity. We trust the sensors, the magnets, the cooling, and the protocols. But when a sensor lies or a warning is missed, the chain of trust breaks. That's what happened. A single faulty reading, misinterpreted, set disaster in motion. The importance of these sensors cannot be overstated. They are the first line of defense against chaos. When they fail, so does everything else. And on that day, the system's trust was fatally misplaced. The failure began with a faulty temperature sensor on magnet QX77b, sending a false cool reading. In reality, a microscopic impurity was generating heat. The adjacent sensor detected the rise, but the AI averaged the data, dismissing it as a calibration issue. The first domino fell silently. Heat built up, causing the superconducting material to lose its property, a quench. Instantly, resistance returned, and colossal current met a barrier, releasing explosive energy. Liquid helium flash-boiled, pressure buckled the magnet, and the containment field died. The proton beam, now unconstrained, slammed into the tunnel wall, vaporizing steel and concrete. The shockwave triggered sympathetic quenches in other magnets. A chain reaction. Magnets failed in a cascade of explosions. Automated safety systems tried to react, initiating a beam dump, but it was too late. The cascade moved faster than any system could respond. The dominoes fell at nearly the speed of light. Our carefully constructed system tore itself apart in milliseconds. Catastrophe unfolded before anyone could react. The energy stored in the accelerator's magnets rivaled that of a loaded jetliner at cruising speed. This potential energy, held in frozen stasis, was unleashed in an instant. The quench was the giant waking up, angry and violent. Events unfolded in microseconds. From glitch to destruction, less than a millisecond passed. Superconductivity is fragile, a dam holding back a vast lake. A tiny crack, a spot of heat, and the dam breaks. The rapid expansion of helium gas ruptured steel and concrete. The stray beam became a cutting torch, boring through the tunnel and into bedrock. In a fraction of a second, the accelerator was transformed into a mangled wreck. The disaster was over before anyone knew it had begun. The cost of a single floor was total devastation. We trusted automation, an AI watchdog, faster and more vigilant than any human. It monitored trillions of data points, designed to prevent failures. But the AI had blind spots. It averaged conflicting sensor data, flagged it as an error, and waited. The AI lacked intuition. It couldn't sense impending doom. Black swan events, unprecedented failures, were beyond its programming. By the time alarms sounded, the disaster was already unfolding. Our system left a fatal gap. Humans too slow, AI too literal. The eHerf disaster was a failure of psychology as much as technology. Decades of success bred overconfidence. We trusted our models and machines too much. We pushed systems to their limits, believing our safety margins were enough. But we failed to account for the unknown. The possibility of a failure mode beyond our imagination. The event was a brutal lesson in humility. Our understanding is always incomplete. The smallest flaw can have cascading consequences. The control room became a scene of stunned silence. The sense of mastery was replaced by vulnerability. The universe reminded us, our journey requires not just intelligence, but humility. The aftermath was chaos. Damaged tunnels sealed, robotic drones sent in first. The images were sobering. A war zone of molten equipment and fractured concrete. A man-made cave carved by a proton beam in 1,000th of a second. Radioactive isotopes filled the air. Cleanup would take years. The financial and scientific cost was immense. Experiments, halted careers, paused, data lost. Public trust was shattered. Questions arose about the risks of such experiments. The investigation was intense, every detail scrutinized. The final report exposed flaws in design, procedure, and risk assessment. Rebuilding the machine was only part of the challenge. Rebuilding trust was far harder. The catastrophe forced us to confront uncomfortable truths. It was a necessary reckoning for science. This event is a timeless story of hubris, our quest to control nature. The particle accelerator was the ultimate expression of this desire. We believed we could box the universe, but nature cannot be perfectly contained. The crisis revealed the folly of our belief in total control. The smallest flaw, a microscopic impurity, was enough to bring down our creation. Our drive for progress must be tempered with humility. Technology is not absolute control, but a partnership with the unknown. Every experiment is a question. Sometimes the universe answers violently. The failure was a costly lesson. There are limits to our knowledge and control. The path to discovery is paved with humility as much as triumph. What must we learn? First, respect. The energy, the complexity, and our own ignorance. We must design for the failures we can't imagine, not just those we can. AI and automation are tools, not replacements for human intuition. The future of safety is collaboration, AI as co-pilot, humans with final command. We must foster a culture that studies failure, not hides it. The eHerf disaster should be a foundational lesson for every scientist and engineer. Failure, honestly confronted, is our greatest teacher. Our quest for knowledge is a journey, not a destination. We must balance ambition with humility, mastery with respect for the unknown. The universe is vast and indifferent. Our survival depends on never forgetting that.